Hey, Assalamualaikum. Good morning, everybody. Um, uh, this in this recording session, we are going to continue with the assembly language programming in 8086. Uh, as you know that an assembly language program is a series of statement or lines, either assembly language instruction or statement called directives. Directives, which pseudo instruction, give direction to the assembler about how it should translate the assembly language instruction into a machine code. So that's why for every uh, microprocessor, they have their own assembly language. It's not the same. And this assembly language need to be uh, compiled into a machine language before being download to the processor or controller. Okay, assembly language instruction actually consists of four fields. You look here, the first one is label, then you have a mnemonic, operand, and command. The last one. Where if you look from the statement here, from the example here, brackets indicate that the field is optional. You are not necessary to have a label. You are not necessary to have an operand or a comma or a comment. And also you don't need to type a bracket. It's not, you don't need to have to put the bracket as shown in the example here. Okay, this is an example of the assembly language. The label field allow the program to refer to a line of code by name. Any name for the labels, then you can refer it later by the name. The label field cannot exceed 31 characters. A label must end with a colon when it refers to an opcode generating instruction. You need to put a colon after you put the character or label. Okay. The mnemonic, the mnemonic or instruction and operands fields together accomplish the task for which the program was written. Okay. You need to have a mnemonic and operand in order to complete. Okay. This is the example. Add ALBL, where add is the mnemonic, ALBL is the operand. Move AX6764. A move is the mnemonic, and AX and the immediate data is the operand. Okay, mnemonic code are add and move, where ALBL, AX, and the immediate data, immediate number are the operands. Okay, instead of you have a mnemonic and operand, where this field also could contain assembler pseudo instruction or directives. Okay, where directives do not generate machine code and are used only by the assembler as opposed to instruction. Okay, later on we are going to look at the directive. By directive, okay, this is the example of instruction. assembly language, okay, where we look at what we mean by directive. Okay, here is considered as a directive defined by all this, and also and proc and procedure actually and end. Okay, these are all the directive. It didn't convert to machine code. Actually, it just show okay, this is the direction of the program. Okay, the command field begins with a semicolon and may be at the end of a line or on a line by themselves. Okay, in the complete line also you can have a comment. You can put a comment in all of it in the single line. The assembler ignore comments. It means that whatever being written after the semicolon will be ignored and did not being compiled to a machine code, machine language. And also comment is considered as optional but highly recommended to make it easier to read and understand the program. If you put a comment, it much manageable, it is structured, easier for you to refer back when you want to, for example, to upgrade the program and so on. Okay, if you look in the example here, after the first two comment, okay, if you look here, this is the first line. It is all the line is a comment. Okay, after the semicolon, you have, and the second also after the semicolon, the whole line is a comment. This directive select the size of the memory model. Okay, you have model small and so on. There are numbers of uh, memory model that you can choose. Okay, I'm not going to discuss all of it in detail. Okay, this is the one marked in red. Okay, these are the options that you can have. Model small means that this directive define the model as small. Then you have model medium. The data must fit into 64 kibytes. The data, only the data, is only have 64 kibytes. But the code can exceed 64 kibytes of memory. This is for medium. If you set for medium. And then you can have a model compact where the data can exceed 64 kibytes, but the code cannot exceed 64 kibytes. Only the data can have more than 64 kibytes. And then you can have large, okay, which both data and code can exceed 64 key. But no single set of data should exceed 64 key. Okay, and so on. Okay, it's not at your level. Actually, we just use the small one. It should be okay. Small option of model. Okay, unless when you are going to further study in details about assembly 86, then you need to at least understand all of the options that we given for model. Every line assembly language program must correspond to an 8086 CPU segment register. Each line need to correspond, need to be to refer to which segment. Okay, you can have code segment, data segment, stack segment, and extra segment. So the simplified segment definition format uses three simple directives. Okay, you can have dot, code. It is the beginning of the code segment, and then dot data and dot stack. It is just the examples. The stack segment defines storage for the stack. Data segment define the data the program will use. Then you can have a code segment which contains assembly language. Okay, and then you can have a directive which reserve 64 bytes of memory for the stack. 64 bytes for the memory for the stack. This is you define a stack with a number 64. Then you start a data segment and then a code segment. The data segment defines there are three data items which you have a data 1, data 2, and sum. In this example, if you look data 1, you define it already. You assign 52 hex. Data 2, you assign 29 hex. Where sum, you leave it. In the beginning, you will leave it. You don't define it yet. But it is only a byte. You define the sum is a byte. Okay, the DB directive is used by the assembler to allocate memory in byte size of chunks. Each is defined as DB, defined bytes. Memory can be allocated in different sizes. Data item defined in data segment will be accessed in the code segment by their labels. Once you define it in data segment, you can access it by the name given in the data segment. Okay, data 1 and data 2 are given initial values in the data section. It's already been given. While sum is not given an initial value, but it will store storage is put aside for it 1 byte. Okay, then we look at the first line of the segment after the code segment. Okay, after point code directive is a proc directive. What we mean by proc? Okay, proc means a procedure is a group of instructions designed to accomplish a specific function. Okay, a code segment is organized into several small procedures to make the program more structured. Okay, it is not you not necessary to to use the procedure, but in the more more detail when you are doing a big project, it is good to have a procedure group. You make it more structured. Every procedure must have the name defined by the proc directive, followed by the assembly language instruction, and close it with an proc directive, where the proc and the AND statement must have the same label. The proc directive may have the option for or near. The operating system requires the entry point to the user program to be for procedure. This is in a more detail how we going to code in the language in EEE226. Okay, some of it I'm not going to discuss in detail. Okay. Before the OS, the operating system pass control to the program so it may execute. It assigns segment register value. When the program begins executing, only code segment and stack segment have a proper value, while the data segment and extra segment value are initialized by the program. You the one that initialize it. Okay, we look here. Move AX at data, where data refer to the start of the data segment. Move GX with AX. Value of AX into a data segment. The program loads AL. Okay, in this example, you load AL and BL with data 1 and data 2. Then X them together and store it in the result sum. This part actually you assign the data segment. Uh, then in the first part actually these two AL and BL you load it with AL and BL with data 1 and data 2. Okay. The next one you add it both and put it inside AL. Later on the next instruction AL will be in the sum. Okay, this instruction is just to set up the return to operating system. Okay, this is one of the simple instruction but complete all the necessary and optional point to be in the assembly language of 1886. You don't need to have all of it. Some of it is optional, for example, the procedure and even the model also. If you don't put A will be, uh, by default will be determined by the processor. Okay, the last instruction move AX 4CH and interrupt 21 return the control to the operating system. Okay. Where the last two lines and the procedure and program. Okay. The label of and procedure main match the label of the prop. This is the main label of the prop. And the last line, second last, okay, and prop main. Okay, it is handy to keep a simple shell and fit it in with the instruction and data for your program. Okay, this is you just can copy this and use for any other function. Okay, if you look at this program 2.1, the list file generated when the program was assembled. We discuss in detail each of the instructions. Move CX05, we load the value of 05 into the CX register used by the program as a counter for iteration or loop. Okay, in here, if you look CX, is used as a counter. Move BX offset data in, we load into BX the offset address of the assigned to data. Okay, if you look here, this is data. Okay. Offset of data in, move bx, offset of data in, where the assembler start at offset 0000 and use memory for the data then assign the next available offset memory for sum, in this case at 0005. Right? Since the data in have 1, 2, 3, 4, 5 bytes. So after 5 bytes, then it will assign for sum. Okay, and then you add AL. Once you put in bracket, this is the offset. Okay, you know that the physical address is the data segment combined with the offset. Okay, data segment here, and then the offset being state defined previously data in. Okay, then add the content of the memory location pointed at by the register BX, and then you put it to AL. Note that the BX is a pointer to a memory location. It's not the value itself. It is a pointer. Point to the memory location where it's stored 25. So if the offset start with 0, value of 25 hex is in the 0000 offset address. And then increment bx, increment the pointer by adding 1 to bx. This will cause bx to point to the next data item, okay, next byte. When you increment, the next location is 12. So program 2.1 explain instruction by instruction. Decrement cx with decrement subtract by 1 from the cx counter, and then set the 0 flag high if the cx is 0. Then you will check. After you decrement, then you check. It is 0 or not. Jump non-zero again will jump back to the label as long as 0 flag is indicating that the cx is not 0. When the cx is not 0, it will not set the 0 flag. Jump non-zero again will not jump only after the 0 flag has been set high by the decrement cx. Okay, when cx becomes 0, this means that the loop is complete and all 5 numbers have been added to AL. Okay, this is a version of program 2.1. Clarify use of addressing mode and show that the 8086 can use any general purpose register for arithmetic and logic operation, where you can use it. Okay, in program 2.2 shows the data segment being done before and after the program was done. Okay, in this, if we look at the label data in data segment is defined as word word means that it is 16-bit, 2 bytes. And the sum also, but it will start at 10, offset 10. 16-bit data, a word is stored with a low byte first. So the data 23AD, the lower address 000 will be 4D, and the higher address 0001 will be 23. It is how we arrange. We call it as a little endian, structure. The address pointer is incremented twice since the operand being accessed is in a word, means that 2 bytes. So you add di with 2, which equal to increment di twice. In the sequence of instruction, it is often necessary to transfer program control to a different location. You need to transfer it to other location. If control is transferred to a memory location within the current code segment, then we use it near. Sometimes we call it intra-segment. Okay? It is within the same segment. If the control transfer outside the current code segment, so it is a far jump. It means the inter-segment, between the segment. Okay, this is the logical address of the code, okay, where you have code segment and instruction pointer. Register always point to the address of the next instruction to be executed. Okay, the next instruction to be executed. They must be updated when a control transfer is executed. Okay, you need to update it first before you can execute it. So in a near jump, the IP is updated and the code segment will remain the same. Since it near, it is within codes within the segment. Okay, since control is still inside the current code segment, so you don't update the code segment. While in the far jump, because control is passing outside the current code segment, so both of code segment and instruction pointer have to be updated to the new values. Okay, both of it can be changed. Conditional jumps have memory such as jump non-zero, jump not zero, and jump if carry, jump carry. If the conditional jump control is transferred to a new location, if a certain condition is met, the flag register indicates the current condition. For examples, if if jump non-zero level, the processor look at the zero flag. It will check at zero flag to see either it is set or it is rise. If not, then CPU start to fetch and execute instruction from the address of the level. If the zero flag is set, it's become 1, it will jump but will execute the next instruction below the jump non-zero. Okay, this is the summarize of all conditional jump instruction. okay, where you have jump absolute, jump not, this one I'm not sure. Jump absolute. Okay, it will JA and JANBE, okay, jump above or not below or no zero. The condition it will check carry flag is 0 and 0 flag also 0. Okay, jump above or equal, jump not above or equal is check the carry flag if either is 0 or not, and so on, all of it. Okay, it will check all the flags. Okay, sign flag, parity flag, overflow flag, sign flag, okay, 0 flag. Okay, this is the summary of all the jump, conditional jump instruction. Where all the conditional jump are short jump. Short jump, what we mean by short jump, the address of the target must be within 100, before 128 bytes and above, plus 127 bytes of the instruction pointer. That is the short jump, conditional short jump. Where the conditional jump is a 2-byte instruction. Okay? 1 byte is the opcode of the J condition, and the second byte is a value between 0 to FF, where an offset range of 0 to FF give 256 possible addresses. It will be ranged between for 256 location. In a jump backward, the second byte is a second complement of the displacement value. Okay, because it is backward negative. It is not negative, it is a backward actually. So to calculate the target address, the second byte is added to the instruction pointer of the instruction after the jump. Okay, if we look here, we have the logical address of the code, and then we have code. If you look here, we look at jump non-zero, why we put it 000D. Jump non-zero is 000D. To calculate the target address, the second byte is added to the instruction pointer of the instruction after the jump. If we look here, this is the address of the instruction pointer of the address of jump non-zero. Jump non-zero was assembled as JNZ000D, and 000D is the address of the instruction with the level again. Okay, again actually here is you want to look back, you refer to the previous examples. Where jump non-000D has the opcode of 75 and the target address of FA. If you look here at 000D here, since it is backward, so FA here, FA is the second complement. 75 is the output of jump non-zero, where FA is the second complement of the address, which you are going to add it with the address the instruction pointer address. Okay. This is followed by sum all, which is located beginning at the offset address 0013. Okay, this is after the jump instruction. The jump instruction is the address is 0011. Okay. It requires another 2 byte to have a move sum all, sum AL, which at location of 0013. Where the IP value of move 0013 here is at the to FA to calculate the address of level again and carry is dropped. Okay, FA in the second complement is -6. So you add the 0013 to -6, you get 000. Okay, it is the next address of the jump non-zero to be added to the second complement of FE. Then you get 000. Okay, calculate a forward jump target address by adding the IP to the following instruction to the operand. The displacement value is positive as shown. Yeah. Jump bit next. Look here, this is jump bit numeric 72 and 06 is the displacement you need to add. So jump bit 0 has the opcode 72. This is the opcode. And the target address is 06. So the IP of 000A and 000B. So the jump is 6 byte from the next instruction. If you look, next instruction is at 000C. Then 00C, you plus with 6, you can get 0012. Hence, which is the next exact address of the next level. Okay, for conditional jumps, the address of the target address can never be more than 128 backward and 127 forward bytes away from the IP associated with the instruction following the jump, mean the next instruction of the jump. And attempt is made any attempt which you want to do is made to violate this rule will generate a relative jump out of the range message. Okay, an unconditional jump transfer control to the target location level unconditionally in the following forms. Short jump, okay, you have in the format jump short level, jump short, and then you have a level where a jump within 128 backward and 127 forward bytes of memory relatively to the address of the current instruction pointer opcode EB. Okay, jump short, the opcode is EB. Where near jump, the default has format, jump, and then we have level. Where it can jump within the current code segment, and the opcode is E9. The target address can be any of the addressing mode of direct, register indirect, or memory indirect. Okay, you can have any of these addressing modes. Direct jump, exactly like a short jump, except the target address can be anywhere in the segment in the range of uh, over 32,000 backward, forward, and backward of the current instruction pointer, current IP. An unconditional jump transfer control to the target location level unconditionally in the following form. Okay. Register indirect jump, you can have the target address is a register. So jump VX, IP will take the VX value. And then you can have memory indirect jump. Target address is the content of the two memory location pointed by the register. Okay, jump DI will place the IP instruction pointer with the content of the memory location pointed by DI and DI plus 1. And then if you can have for jump in the format jump for pointer level register, a jump out of the current code segment where the IP and the CS are both replaced with the new value. The instruction pointer and code segment are can be replaced. Okay, we have the call instruction is used to call a procedure to perform a task that need to be performed frequently. Okay, you need to have a subroutine where you require frequently to call the subroutine. The target address could be in the current segment, in which this case it will be near call, or outside the current code segment, which we call it as a, you can use it for call. The microprocessor saves the address of the instruction following the call onto the stack. Okay, that's why that is one of the purpose, the reason of using stack. Okay, where you save the address of the instruction following of the call onto the stack temporarily, because after you came back from the call, then the value of the address from the stack will be put onto the code segment and instruction pointer to know where to return after executing the subroutine. In the near call, so only the IP is saved onto the stack, while in the far, there will be code segment and IP that's saved onto the stack. Okay, for control to be transferred back to the caller, the last subroutine instruction must have a return instruction. For near call, IP is restored. For far call, CS and IP going to be restored. Okay, so assume that SP, stack pointer at FFFEE. Okay, when you have a call, if you look in this example, the next instruction, okay, this is the value. The next instruction, if the call is near call, so only the IP will be saved. It is a far call, then both the the segment and the IP will be saved. Since this is a near call, then only IP saved in the stack. Okay, look, IP will be saved in the stack. Okay, FE, then it will decrement by 1, restore the first byte, the higher byte, and then increment by 1, you store another byte. So the IP address 0206, which belong to the move AX instruction, is saved onto the stack. Means the next instruction after call. The last instruction of the call subroutine must be a return instruction where it directs the CPU to pop back the two top bytes on the stack of the stack into the instruction pointer and resume the executing at the offset address 0206, where the number of push and pop instructions which alter the stack pointer need to be matched. It must match. Okay. When you push, then you need to pop. Okay. You have to. Otherwise, it will crash. The system will crash. So it is common to have one main program and many subroutines to be called from the main program, where each subroutine can be separate module, tested separately and brought together. If there is no specific mention of far after the directive prop, so the default is near. The procedure is near.